cursor? Or...
I don't see it right now.
Okay, so we'll try.
Okay.
Okay, so first I would like to thank the organizers for this nice opportunity. So I will try to convince you that there is indeed a band inversion in the system, although I guess most of you are convinced because there is a lot of evidence by now of both the direct surface state and even some bound states in the cores of this material. So it seems like a topological superconductor. But as you will see, it's quite surprising that we can see a band inversion in such a band structure as seen in this material. So just to make the name of the compound more friendly, let's call it FST, okay? Oh, there's some issue. Okay, so this work is a collaboration between the group of Moito and Deria in the Ohio State University, Bingai Yan at the Weizmann Institute, who did some DFT calculations for us, and myself. And the people that really did the work here are Imanshu Loani, who did the ARPES work, and Tamagna Azra, who did a very nice tight banding model that I will show. And I just want to mention that all the data we show was taken at the Diamond and FeSe synchrotrons. Okay, so the starting point is this prediction by Wang et al. From 2015 that using DFT have shown that when some of the selenium is substituted by the tellurium, we get for some reason a much stronger dispersion along the KZ direction. And he predicted that there will be a crossing between a very dispersive PZ band and the d orbitals that form the pockets around the gamma point. And one of these bands is supposed to mix with the PZ, and then there will be basically an opposite parity of the valence band at the gamma and the Z points, which is exactly what you expect from a 3D topological insulator or a Z2 topological superconductor insulator. So this was, for us, actually, this was a very weird prediction because at that time we were working with this compound, and this compound is really extremely 2D. So it's very hard to expect something like that. But soon, or at least 2 years ago, there were very nice demonstrations that actually were indicating that this is indeed a topological superconductor. The group of Hong Ding and Shixin showed very nice Dirac-like surface state with all, and they even showed that it's spin polarized. And soon later, they used an STM to show something that looks really like a zero bound state in the core of the vortices in this material. And it's very, very hard to, let's say, explain these features in any other way except topological superconductivity. But why this result seems surprising? To see that it's very informative to compare the ARPES and the DFT predictions. So I think the first paper that was showing that there is really a systematic inconsistency between the DFT and the ARPES was the work by Anna Tamai, where they showed that to somehow fit the DFT band structure, you need to renormalize the bands by something which is between a factor of 4 and 20. on top of that, we later on showed that the Fermi energies in this material are extremely small, of the order of 10 millivolts. So they are so small that you can even at some extreme samples think about this system as a BEC superconductor, where delta is really of the order of the Fermi energy. So the DFT prediction seems to, they for some reason, they are holding when you are thinking about the KZ dispersion, but they are very different from the experiment when you look at the planar dispersion. So we decided to look more carefully, to measure more carefully the band structure along the KZ direction. So these are the samples we are using. These samples we grow at my lab. I think that they are quite similar to other samples that are used by other groups. For these experiments, we did a lot of, we did very careful oxygen annealing to try to minimize as much as possible the excess iron, which leads to some magnetism. And all the data I will show is taken for a x equals 0.4 substitution, and TC of the sample is something like 14.5, 15 Kelvin. Okay, so what we are first, I would like to show you how we extract exactly the band structure. So this is a typical ARPES scan at 22 eV, and you can immediately see these two hole-like bands. For each of these bands, we basically take cuts, many cuts at different energies, and from this momentum distribution curves, we can extract very nicely, just using a parabolic fit, we can extract the Fermi energies of these two bands. So here you can see one band which is basically crossing the Fermi level. We call that band alpha 2, and this band creates a pocket around the gamma point. And you can also see alpha 1, which is a pocket, which is a band which is approaching the Fermi level but never crosses it, and it approaches to about 15 to 20 millivolts from the Fermi level. And this is exactly the band that is supposed to mix with the PZ band. Now this is it's a relatively complicated band structure because there are many pockets and many orbitals. So when we change the polarization and the orientation of the samples, we can get a lot of information about the orbital content of these bands, and these will be important. So for example, here you can see that just by switching the polarization, we can completely get rid of this alpha 2 band, which would be very useful for looking at this band inversion. Okay, so next we would like to see if we can see the surface state. So all the data that basically was focusing on the surface states in this material was done using a laser, where the photon energy is very low and the momentum resolution is extremely good. The same was actually shown in the previous talk, data by Peter Johnson. But if this is really a surface state, then it should be present at any photon energy and at any KZ, right? Because it's if it's a surface state, it cannot depend on KZ. So what we do here is we are looking at the top of this alpha 1 band using a lot of many photon energies. We scan here between 30 and 100. And you can see that at the binding energy of 10 millivolt, we always see some intensity. So this is an intensity which lies just above the top of this alpha 1 band. And the fact that we see it for any photon energy is encouraging, because this is what you expect from a surface state. In addition, we see it's not dispersing. So we cannot, in the raw data, it's very hard to see this Dirac cone, but just by taking the second derivative, you can see that indeed there is a faint Dirac cone-like feature just lying on the top of this alpha 1 band. To show that it's not dispersing, what we do is we we take cuts at different energies, and we look at the momentum, at the width in the momentum of these peaks, and you can see that there is also always a minimal width to this peak, which is at about 8 millivolts, and we assign this minimum with the Dirac point, which is actually in agreement with the work of other groups. So there is a surface state, and the Dirac point is about 8 millivolts below the Fermi level. Okay, so next we can now look at the dispersion along KZ and try to compare it to the DFT prediction. So to do that, what we do is we, as I said, we vary the photon energy, and using the simplest assumptions done in RPES, we can relate this photon energy to the momentum normal to the surface. And what we find is that indeed this alpha 2 creates a pocket, and there is some dispersion along KZ of about, the bandwidth is about 15 millielectron volt, as expected, very small compared to most metals, let's say. The situation is even worse for this alpha 1. Alpha 1 is completely flat. So within our momentum resolution, I would say that there is no dispersion along KZ for this alpha 1 band. And to show how, and to see how unusually this thing is, you have to compare it to this DFT calculation shown here, where this alpha 1 is expected to have a bandwidth of about 600 millielectrons. So in principle, this flat band, this is exactly the band that it's supposed to go to undergo this band inversion. So this raises the question of how can you get a band inversion along KZ in a band which is completely flat along KZ. So to try to understand these features, both the flat band and the fact that experimentally it seems that indeed there is a band inversion, Tamagna composed a very nice kind of tight banding, which is supposed to be the minimal model to see these effects. What we keep basically 3 orbitals, the PZ and the DXY, XZ, YZ orbitals, and we start from a renormalized bandwidth, which we assume is due to interactions. But we are trying to keep the ratio of the bandwidths of the PZ and the D orbitals as found in the DFT. So assuming that the interactions start by renormalizing the bandwidth in a uniform way. You can think about it in this way. Okay, so this is the dispersion before we turn on a spin-orbit coupling. When we turn first a spin-orbit coupling between the d orbitals, we get this splitting that is responsible for alpha 1 and alpha 2. We use here spin-orbit coupling, which is very small. It's only 8 millivolts, but because the bandwidths are so narrow, this 8 millivolts is not negligible compared to the bandwidth, and it plays an important role. Now, when what DFT and the model here tells you is that when the PZ band crosses these 2 d orbitals, it can hybridize and mix only with one of them. This is a result of the symmetry of the underlying crystal, and what is the band which is supposed to mix with the PZ is alpha 1, as I already mentioned. So now let's add the spin orbit and allow it to mix the P and D bands, And we already get something which is similar to what we see in the experiment. So the effect of the spin orbit coupling is to open a gap and also to considerably flatten the alpha-1 band. Now, according to this model at least, there is indeed a band inversion. You cannot see it in the dispersion of alpha-1, but you indeed get that the parity of alpha-1 changes when you go between the gamma and the Z points. So can we now experimentally verify this idea? So to do that, we want to use the selection rules of RPES, because now we expect that at the asymmetry points, the character of the alpha-1 will be pure. So we expect that at the gamma point, the band will be purely made of d orbitals, and at the Z point, it will be purely a p orbital. So if we can somehow arrange the experimental, let's say, geometry in such a way that the RPES will pick, for example, only the D or only the P, we could maybe see a difference in the intensity between these 2 points. Okay? Okay, so this is a summary of the selection rules for this symmetry. This is quite involved. So for the purpose of I think this talk and this experiment, we are measuring along the gamma X orientation of the crystal, and we use vertical polarization, linear vertical polarization. And in that case, the selection rules are quite simple. What the selection rules tells you is that only the dxz component of alpha-1 should be visible using this geometry. So now, if you really want to understand all the selection rules, it's I think summarized very nicely in this paper. So now we have, in a sense, a way or a prediction that we can go and test. So we can now, again, vary the photon energy as we did before, but we are not just going to look at the position of the peak, but at the intensities. We measure only at normal emission and along the gamma X, as I said, where we expect that the intensity will be higher at the gamma point compared to the Z point. Just because at the Z point, we expect the orbital character to be mainly PZ, which is not allowed at this asymmetry by the selection rules. Okay, so this is now the data. So I show you basically an image which is composed by, that is stacking a lot of energy distribution curves, taking at normal emission at different photon energies. And you can see here that we managed to basically scan more than 3 Brillouin zones along KZ. You can also see the EDC at the particular photon energies, and you can indeed see that the intensity of this peak, the green peak, which is the top of alpha-1, changes. And also, it seems like the intensity of the surface state, which is here marked by this black line, also changes. Okay, now, when we try to extract useful information from a plot like that, the main issue here is the normalization, because when you do spectroscopy, if you look at features and energy, so then you are safe. But if you are trying to look at intensities, this can many times be misleading, because the intensity depends on many factors. We scan here the photon energy on a very large range. So the efficiency of the beamline changes, the cross-section of the different elements changes, and it's kind of risky to look at the intensity, and it's much safer, in this case at least, to look at the intensity ratio. And why is that? Because the surface state is two-dimensional, it cannot depend on KZ, and it means also that the orbital composition cannot depend on KZ. So in a sense, by normalizing the intensity at the top of alpha 1 by the intensity at the surface state, and we choose to do it at the Dirac point, 8 millivolts below the Fermi level, hopefully we get rid of many of these factors that strongly depend on the photon energy. So when we do that, we indeed find a very nice oscillation of this normalized intensity. So what I'm showing here is exactly that. It's taking the intensity at this green line, which is the top of alpha 1, and divided by the intensity at 8 millivolts, which is marked by this black dot line. And you see the intensity is oscillating in such a way that it's always maximal at the gamma point and minimal at the Z point, which is in good agreement with this prediction of the model, because we know at the gamma point, the orbital, the alpha 1 is purely D, and at the Z point, it's purely P. So the fact that we see these clear oscillations, which is always maximum at the gamma point and minimum at the Z point, and we can follow that over 3 brilliance zones, it's a very, I think, robust indication of indeed a band inversion. Okay, so this is the story. Just to conclude, I think using RPES, we can reconcile some of these seemingly contradicting facts. So indeed, there is a very strong signature of topological superconductivity in this material, but the DFT is too simple to explain the situation. There is no dispersion in KZ, so it cannot just be a strongly dispersive PZ orbital crossing D. And this is due to these very strong correlations in this material. But nevertheless, using this simple model, we can, I think, understand it. And by looking carefully at the intensity and using the selection rules, we can even show that there is indeed a band inversion. So we think this is a very strong evidence of a topologically non-trivial bulk band structure in this material. And I think the most interesting part here is that it shows that the symmetry protected topological invariants somehow survive this strong interaction. And this is a case where the interactions are really strong and completely change the band structure compared to the DFT. But in some mysterious way, the band structure somehow remembers the pair band structure, and the invariants remain, these topological invariants remain intact. And then this entire story is summarized in this PRB paper. Thank you.
Thank you very much, Amit, for this very nice talk. Any questions from the audience? Peng Cheng?
I guess I was curious. So I'm not an expert on this in this area. So does that agree with previous experiment or not? Previous description?
You mean if the data agrees with different?
Well, I mean, I guess you're saying that there's no KZ dispersion, right? I guess Chongjun was saying that Peter Johnson sees this, right? I mean, sees the inversion symmetry and gap opening. Do you see the same thing? Or
Yeah. So okay. So we see. You mean now the magnetic gap? So
yeah, I mean the gap at the Dirac point.
No. So with this kind of RPS data, I cannot even try to see such a small gap. This is so Peter's data was taken with a laser, where you get a very high resolution, but only at one point. So if you really want to learn about the properties of the surface state, maybe a laser is a better solution. Here we mainly wanted to understand the relation, or let's say the properties of the bulk.
Oh, I see. So okay.
This is in a sense a normal set of data.
Okay, thank you. Yeah.
But that may just add from Photon. I guess the consistency is that there is the band inversion from this analysis, which is
yes.
Yeah, so that aspect.
In that sense, it's very consistent. I agree.
Yichen? Yes. So the first question I have is for the calculation part, actually. So when you say like you constructed a minimal tight banding model, and after adding the SOC, like the bands, one of the bands can hybridize with each other, the other one cannot. I just wonder. So because in the end you get such a flat band along KZ for the alpha one band, I just wonder, in that calculation, did you just only add the SOC, or you also include some other like interaction effect to renormalize the band, the alpha one band?
No. So the renormalization of the bands is done before, in a sense, if you want, including the spin orbit coupling. So the fact that alpha 1 is flatter than alpha 2, it's just because of the spin orbit coupling. There is no other interaction.
I see.
The fact that alpha 2 is flatter than the DFT prediction, this is put by end, assuming that this is a result of the strong interactions.
I see. Okay, thank you. So, and the second question is, so in this slide, we can see the oscillation of the alpha 1 band with the photon energy. I just wonder, so if I remember correctly, the space group of this FST material is also is like tetragonal crystal lattice, right?
Okay.
Yeah, I just wonder, like this kind of oscillation in different photon energies, could that also like be quite general in other KZ dependency, in other tetragonal, even if it's not iron-based superconductor? Like, for example, it's also a tetragonal crystal lattice, so it almost have the same planar geometry. And if you measure it along gamma x direction, would you also expect, like, because just simply because of the geometry, so you can have the similar kind of?
You mean these are oscillations in the intensity, not in the dispersion?
Yeah, I mean the oscillation in the intensity because of the matrix element effect. So I just wonder if we have other kind of tetragonal crystal, even it's not in this family, do you think that's could be a general case in KZ dependent experiment?
No, I don't think it's a general case. I mean, no, I'm not expecting that in a let's say in a different iron-based superconductor where there is no band inversion. But I don't have data to show you that it's different in a different system. But I don't expect it. It will be very surprising if this is a result of the structure itself.
I see. So the main ingredients, you have to have the band inversion along this gamma z KZ direction.
Yes.
I see. Thank you.
Qimao?
Yeah, I mean, nice talk. I have two questions just to make sure that I understand, to make sure I got the details right. The first is, in this picture shown on the top left, alpha 1 is below the Fermi energy, and alpha 2 is primarily above the Fermi energy, right? So am I understanding that this oscillation concerns the alpha 1 states?
Only alpha 1. Alpha 2 is forming a pocket, so
right. You have a small pocket near gamma, but
right.
But you don't.
Experimentally, you can never see the top of alpha 2.
Right. So the band inversion, the conclusion about the band inversion is a statement about alpha 1.
Yeah.
Okay.
Yeah.
So,
also according to the DFT, only alpha
fine,
1.
Yeah. So that led me to the second question, which is perhaps also somewhat details, but it might be relevant. So I can understand that the D states are strongly renormalized by the interactions. And there's a variety of ways of thinking, orbital selective, etc. But for this DP inversion to end up to be nearly flat dispersion, it seems to me that there could be some fine tuning that's required for the dispersion of the renormalized PZ states that doesn't crash down all the way to very low energies below the Fermi level. And instead, it should also crash down to, as gamma goes to Z, the PZ dispersion should be approaching towards something within 20 MeV, etc. scale. And yet, I guess the question that's in my mind is that I would have thought that the interaction renormalization to the PZ states would be much more minimal compared to the interaction renormalization of the D states. And so I'm back in my mind, I'm just wondering, now, of course, in the analysis, you put in the renormalized dispersion, so it's very nice. It comes out, but I wonder whether there's some degree of naturalness that one could raise question.
I think in the paper there is an appendix showing the spectrum for different parameters. So this is not exactly fine-tuned. At least in the term of when you think about RPS, I cannot see the unoccupied part. So even if the PZ is very broad, as long as its bottom is not very far from alpha 1, alpha 2, I will get the same result.
Right.
So yeah, so I cannot really say experimentally even what is really the bandwidth of PZ. Experimentally, you don't see PZ. You see a flat band, and its orbital component is changing gradually when you move between gamma and Z. We don't see. I never get to see the P band when it's pure, which is more around the zone center, the gamma. Yeah. So I don't know what is the real band. This is the truth.
I mean, I think I agree with that. I think what seems to be happening is that, well, interaction renormalization is not just the bandwidth of the D states. It also changes the Fermi energy with respect to where it's located with respect to the band. So there seems to be some requirement that the interactions should also push the Fermi energy to be pretty close to the bottom of the PZ band. And maybe that's natural, maybe not. It's an interesting question, at least.
Yeah, okay, I don't know.
Yeah, thank you.
But I just chime in for that, Ismail, I guess, because then we need some sort of a orbital dependent shift, because according to DFT, I think the bottom of the PZ band and then the XY band are quite separate in energy.
Yeah, no, there's no problem. We can give you the orbital dependent shift. That's a big thesis from Rong you and myself. But I'm just we never thought about the P states, how that renormalizes, and I would expect that interaction will not affect the PZ states that much, except that the Fermi energy is being moved around. And so to me, it's a very interesting question: why the Fermi energy should be pinged close to the bottom of the PZ band.
I see one more hand, Andreas.
Hey, I have a question regarding just this plot you have been showing, where you follow the intensity basically of the XZ, YZ orbital and show that the intensity is lower at the Z point than at gamma. Now, have you made an attempt to actually also do the opposite, to detect the PZ orbital? So to look at another polarization property where you can actually detect PZ and see that kind of opposite behavior, namely the
I see what you're saying.
Than at gamma.
This is more complicated, just because of the selection rules. This would be very difficult to do.
I'm just asking because now in principle there is the possibility that at the Z point there might be some other orbital mixed in. I have no kind of suggestion what is actually happening, but I mean, let's suppose that x squared minus y squared orbital is stronger at the Z point.
But actually,
it could also be the same signature in your data.
I think I see your point, but so at least okay, we know which orbitals are around. So actually, this geometry is perfect for that because you cannot see this geometry. You can only see the DXZ. So what I see, the fact that the low intensity at Z is because of the missing part of this DXZ.
So you just see the missing part of the DXZ.
So
you cannot detect the appearance of the PZ.
Right, exactly. I don't see the PZ. I cannot see. I just normalized by the surface depth, which is some. Maybe it could be calculated, but for me it's unknown mixture of these two bands. But alpha 1 itself, I only see the component which is this TXZ in this geometry. And any attempt to see another band then I will face the problem you're raising, because then I can see more than one orbital.
Okay, thank you.
Great. Any other question? I guess we can also, I see there was one question in the chat. I guess that was for Chongjun's. We can open up the floor for any questions. So I don't know if Chongjun is still, maybe he's not there anymore. Sorry. Okay, anyway, any other questions? If not, I guess let's thank both Chongjun and Amit very much for their time and for this very interesting discussion.
Thank you.
I can make a comment on the last question, if time permits.
Yep.
So I guess the question of mixing with the DXZ has to do with which orbitals are allowed to mix with the alpha 1 and the alpha 2. Now, the lower band, which is the alpha 1, can mix with PZ, but the lower band is not allowed to mix with dx square minus y square or dxz minus y square. Those two can actually mix with the upper band. So the other ingredient in this modeling that went in, that the band flattening is because of SOC-induced spin-orbit splitting, does not work for the DXZ, DXY or the DX square minus y square orbitals. So if we admit the possibility that this is a band inversion with DXZ-YZ orbitals with a DXY or DX square minus y square, we then have to grapple with the question of then why is the band flat? So that was my 2 cents on that.
So can I just add, so even though you cannot see the XZ band, do you still see a peak even though it's weak? So meaning that the band position is still there?
We never see another band crossing into the field of view, if that's what you're asking.
So I mean, when the intensity is low, say around the Z point, do you still see a weak peak due to the residual XZ spectral weight?
Yeah, I think you can see it here, for example. It's if you look at around 44 EV, it's not zero. There is some background, so I guess also the selection rules are not perfect. So, but there is a very significant variation in the intensity.
So could I just add stuff along this direction? I think during the symposium, there was a talk by Pen Zhang, who used to be at IOP, now at in Tokyo. And I had the impression that he was also saying that in ion selenium thorium case, as opposed to be lithium 111 case, that what is seen in the bulk spectrum from gamma to Z is quite flat. And I, since they are not here, time zone doesn't allow. I was just wondering, Amit and anybody else, this nearly flat alpha 1, is that also seen in other RPES groups data? If you don't mind commenting.
For this system, for the FST?
Correct, yeah, like near 50-50, which is what you're doing.
So I think, I don't know if this was addressed, but if you look at, actually we checked that. So different routes measure a different photon energy. Usually not systematically, but if I collect all the data from other groups, I think we always see the position of the top of alpha 1 more or less at the same place. So this can move between, let's say, 15 and 20 milli-eV below the Fermi level, not more than that.
But the observed bandwidth is very narrow for gamma to Z.
So for that they would have to measure at different photon energies.
I see. So the point that you've done the systematics of wide range of photon.
But this is because I was looking for that question. Usually, yeah. So.
Okay, great. Yeah, thank you. Yeah.
So with that, I guess we will conclude the seminar today. Thank you all very much for coming. We'll have another one in.
Good to see you, Amit. Yeah.
Yeah, thank you, Amit. Thank you very much.